Hello everyone. In this video, I'll walk you through what happens when we increase the drain to source voltage. So we in the last till the last video, we had come at a point where your drain to source voltage, we had given a small value for VDS. That's the drain to source voltage. We'll now increase the drain to source voltage and see what happens. Okay. So the first things first. Till now, what we have learned is we had this particular condition which was VGS equal to 1 volts, VDS equal to 0.05 volts, and your threshold voltage was 0.45. Okay, so let me quickly revise few things over here. We had given this thing as an x-axis. Okay, and the gate to source voltage, or VGS minus V of x, was the voltage at each and every point on the channel. Okay, so let's try to generalize this for this particular condition and say that now your channel voltage is VGS minus VDS. So under this condition, your VGS is 1 volts, your VDS is 0.05 volts, your VT is 0.45, so your channel voltage will be 1 volts minus 0.05 volts, which is 0.95. Okay, in this particular state. Now what we'll do, we'll increase the drain to source voltage gradually and see what exactly happens. Before that, one last thing, we had seen this particular threshold voltage, the concept behind the threshold voltage, and this was the voltage at which your surface inversion happens. Okay, and the reason we were able to see this particular channel, it's because your channel voltage VGS minus VDS was greater than threshold voltage 0.45, and as a result of that, you were able to see the channel. Okay, so now just imagine what will happen when we increase this particular value of VDS. So let's do that now. So we have drawn some tables over here. We have this VGS thing which is kept constant. VGS column is kept constant. The threshold voltage column is kept constant. Okay, and you have this VDS column where VDS is being increased from 0.05 till 0.95 at steps of 100 millivolts or zero point 0.1 volts. And by the way, these are the inputs that you can directly feed to a spice engine, and the engine will do it for you. But the important part is what happens when the VDS increases, when VDS is gradually increased. The concept behind that should be very well understood to understand the graphs that will be created out of spice. That's where we are creating a background over here. Okay, so you have your VGS which is constant at 1 volt, you have VDS which is being increased from 0.05 till 0.95, and you have your threshold voltage which is kept constant. So till this point, till a point where we were over here, we started from 0.05 millivolts in the previous videos, and we will increase the drain to source voltage from 0.05 till 0.45. And we observe that during this region, during this red marked area, your VGS minus VDS, which is your channel voltage, is always greater than your threshold voltage. And as a result of that, you see a conducting channel from source to drain. Okay, but there might be a case where your channel voltage will just go below your threshold voltage and things will drastically change over here. So we'll move to that in some time, but before that, to conclude this discussion, you have this point at 1 volts because your VGS is constant at 1 volts. Your this point is at 1 volts minus VDS, which is VGS minus VDS. So technically this point is at this point will be at 0.95, 0.85, 0.75, 0.65, and 0.55 volts respectively. And your channel voltage tends to be greater than VT, tends to be greater than threshold voltage, and as a result of that, you still see a conducting channel. Now let's mix two particular concepts at this point where you have your VDS as 0.55 volts. Okay, you have your channel voltage VGS minus VDS as 0.45 volts, and VGS minus VDS, which is the channel voltage, this point is at 0.45, your threshold voltage is at 0.45. Now things will change. So what happens now, this point is at 1 volt, this point is at 1 minus 0.55 volts, which is 0.45 volts, and that's the value of exact threshold voltage. So one point is greater than threshold voltage, and this point is just equal to threshold voltage. Okay, and in some videos, which are in the past videos, we have learned that the voltage at which surface inversion happens is referred to as threshold voltage. So what does that mean? This particular voltage is, this particular region of your MOSFET is at a voltage where surface inversion just happens. This point of your MOSFET is at a voltage at which your gate voltage is actually greater than threshold voltage, and your surface inversion has already happened. So over here the surface inversion is just about to happen. Over here the surface inversion has already happened. So there is a mix and match of two different concepts over here, and as a result of that you see the channel to getting disappeared. Okay, so the channel that we created by applying VGS, which was greater than VT, under the absence of VDS, we had created some channel. But just as you apply the VDS and increase it, you see, because of the mix and match of two different concepts, where your channel voltage is supposed to be is supposed to be greater than threshold voltage for this channel to appear. Now because of the same condition, you'll see the channel getting disappeared towards the drain region, because the gate to channel voltage, the channel voltage, which is VGS minus VDS, that just doesn't satisfy the threshold voltage, the surface inversion condition. And as a result of that, you see a channel getting disappeared from this point, but the channel will be still present over here. So let's triangulate this one, something like this. You see the channel being present at this point of time, at this point of your MOSFET, but at this point you just see the channel getting disappeared. And this thing will get even worse when you increase the VDS voltage. Okay, so this phenomena of channel getting disappeared is referred to as pinch-off phenomena. Okay, so it has, this particular phenomena has just started, and as a result of that your channel begins to disappear. But what does that mean? Does that mean that the current stops flowing? No, that doesn't mean that. I'll come to that point in some time from now. This just, you still have a potential difference from this point to this point, so there will be a current flow, but the linearity of the current flow will just change from starting from this point. Okay, and I'll come to the linearity, I'll come to the models for the drain current after this particular value. But let's try to conclude this part. So at this point of time we have seen the surface inversion, just the surface inversion condition being hampered, and as a result of that, this area which was greater than VT now went less than VT, or is at equal to VT, and as a result of that your pinch off phenomena started, and your channel is now beginning to disappear. And let's see how does this phenomena goes and extrapolates to itself when you try to increase the drain to source voltage. So in this particular section, where your drain to source voltage is phenomenally high, it's 0.65, 0.75, 0.85, 0.95, your VGS minus VDS goes less than threshold voltage. And this condition means that you will not see any channel present over here. And as a result of that, the area near the drain, in this particular area near the drain, your channel just vanishes, it disappears. Okay, so there is no channel near the drain area, but there is some channel present in the source area, and this condition is referred to as saturation region. Okay, and saturation region happens whenever, or a pinch off condition happens whenever your VGS is less than, when VGS minus VDS is less than equal to VT, and this is the condition when your MOSFET saturates. Basically it can't do anything from this point of time. Okay, so very soon we will be converting this particular condition into a model. We'll be converting this particular condition into a current equation, and we'll feeding that particular current equation, or feeding that current model to a SPICE engine. Okay, so we have analyzed one particular condition where your VGS is equal to 1 volts, which is 1 volt constant, and we increase the VDS slowly from 0.05 to 0.95 volts. Okay, so during this condition the linearity of the current was maintained. During this condition and this condition, what will happen to the current equation, we'll look at in some time from now. But before that, the phenomena that we just saw, this is a very important physics phenomena, that your channel begins to disappear at a channel voltage which is less than equal to VT. Okay, so this condition is a very important condition. In the previous videos also, we came up with some equations with saying that should be XYZ should be greater than equal to VT for current to flow. In this case, this is a very important model where we say VGS minus VDS should be less than equal to VT for the pinch off condition to happen. Okay, so starting from this point, we'll try to derive the current equation. Since I'm already running out of time, we'll try to derive the current equation, we'll try to build the current model and feed those current model to the SPICE engine. We'll feed this particular voltage conditions to the SPICE engine and see what happens. So let's try to do all this in the next video. Thank you.